50 million years ago, the most dangerous predator in Earth's oceans was a whale. Not a shark, not a sea reptile, a whale up to 60 feet long, which is about 18 meters, with a body that moved like a sea serpent and jaws built to tear apart prey large enough to fight back. Everything we associate with prehistoric oceans came later. Megalodon had not appeared. The great sharks of the modern world did not yet exist. This predator ruled warm seas that no longer exist, across an ocean unlike anything alive today. Its bones were so strange that the first scientists who uncovered them believed they had found the skeleton of an enormous marine reptile. It still carried small hind legs on the outside of its body, a reminder that its ancestors had once walked on land. It hunted without echolocation, finding and killing prey through senses that scientists are still trying to fully understand. Its victims included the young of other early whales. Fossil skulls still preserve the bite marks, revealing attacks carried out with remarkable precision. For roughly 15 million years, it stood at the top of the ocean food chain. Then it disappeared completely, leaving no living descendants behind. In this journey, we're following the rise and disappearance of one of the most successful predators the oceans have ever produced. The stage on which this story unfolds belonged to an Earth that no living creature has ever seen. Between roughly 56 million years ago and 34 million years ago, during the Eocene epoch, the ocean settled into a form unlike the one surrounding the continents today. It wrapped itself around the planet with broad connections, generous coastlines, and warm expanses that reached far beyond the tropics, creating a marine world whose foundations would shape everything that followed. Across much of the globe, shallow seas covered regions that are now dry land, places where wind now moves across desert stone, once rested beneath clear water lit from above. Mountain ranges that would someday tower into the sky still waited beneath the surface, hidden beneath sediments gathering grain by grain. Continents stood in different positions, leaving wide marine corridors through which water, nutrients, and life drifted with remarkable freedom. The ocean felt less divided, less confined, and more continuous than at any later chapter of Earth's history. Its warmth defined every layer of that environment. Tropical sea surface temperatures reached approximately 35 degrees Celsius, or 95 degrees Fahrenheit, exceeding anything measured in the tropical oceans of the modern world. That warmth extended far beyond familiar boundaries, softening the contrast between equatorial waters and the distant polar regions. Ice held little influence over the planet. No great continental ice sheets locked away vast stores of water, and without them, sea levels stood dramatically higher than they do today. Those elevated seas spread across low-lying continental margins, creating immense shallow shelves bathed in sunlight. These broad marine plains became some of the richest biological landscapes the planet has ever sustained. Sunlight penetrated easily through much of the water column, nourishing microscopic plankton that multiplied in extraordinary abundance. Every bloom became food for countless drifting animals, which in turn supported schools of fish, swift hunters, and larger predators. Energy moved upward through the food web with remarkable efficiency, creating an ecosystem whose productivity exceeded that of modern tropical seas. Every current carried opportunity. Every coastline blended into another productive habitat. Estuaries, lagoons, broad continental shelves, and open coastal waters merged into one enormous living network. Rather than isolated pockets of abundance separated by barriers, much of the Eocene Ocean functioned as an interconnected nursery where life expanded across immense distances. Prey animals occupied nearly every available niche, supported by environmental stability that endured for millions of years. Within such conditions, survival rewarded adaptation with remarkable speed. Marine reptiles that had dominated earlier chapters of Earth's history had already disappeared, leaving ecological space unclaimed at the highest levels of the food web. Sharks remained important hunters, yet none occupied the overwhelming position that later generations would associate with the greatest predators of the sea. The upper reaches of this ancient ecosystem remained open, waiting for a newcomer capable of exploiting every advantage offered by this unusually generous world. That newcomer did not emerge from the depths. It arrived carrying lungs filled with air and a history rooted on land. Descended from mammals whose ancestors had once walked beside rivers and coastlines, it entered these warm waters during a period when every environmental condition favored experimentation. Rich prey, connected oceans, and expansive shallow habitats created an evolutionary landscape where each successful generation pushed farther from the shoreline than the last, until the boundary between land and sea no longer mattered. By the passage of only a few million years, that wandering mammal had climbed beyond every other hunter in the ocean, and understanding the form it took at the summit begins with setting aside every familiar image carried by the word whale. A familiar word can sometimes conceal a completely unfamiliar shape. The name whale carries an image polished by the living oceans of today. Broad backs rising through rolling water, powerful tails driving compact bodies with graceful certainty. Basilosaurus belonged to that same evolutionary lineage, yet almost every expectation attached to the word dissolves the moment its skeleton is assembled. It occupied the body of a whale only in ancestry. In appearance, it seemed to belong to another chapter of life entirely. The largest known individuals of the North American species reached nearly 18 meters in length, which is about 59 feet. The closely related Egyptian species attained comparable proportions, stretching through the ancient sea with nearly the same extraordinary dimensions. Even these measurements fail to capture its true presence, because the eye naturally imagines a creature growing larger in every direction. Basilosaurus did not expand into a rounded giant. It extended outward, becoming astonishingly long while remaining unexpectedly narrow, a proportion with no genuine counterpart among living marine mammals. Much of this remarkable form came from the architecture of its spine. The vertebrae through the middle of the body were elongated far beyond those of any modern whale. Instead of compact building blocks supporting a sturdy frame, each bone resembled an extended segment, producing an animal whose proportions approached those of an immense eel more than those of any familiar cetacean. The spine itself became the defining feature, carrying the body forward in a continuous sequence of stretched vertebrae that seemed almost excessive in their length. Those vertebrae also possessed an unusual internal structure. Rather than being densely solid throughout, much of the interior contained spaces filled with fluid during life. This reduced overall weight while sacrificing some of the stiffness that modern whales depend upon when generating tremendous force through their tails. The skeleton favored flexibility over rigidity, suggesting an animal built for movement unlike anything now crossing the seas. At the front of this elongated body rested a skull that measured roughly 1.5 meters, that is nearly 5 feet, from its forward tip to the back of the cranium. Long, low, and remarkably narrow, it presented very little of the rounded profile associated with living whales. Its jaws extended forward with mechanical efficiency, providing ample room for large muscles and an exceptionally wide gape. Every proportion of the head hinted at an animal shaped around the demands of seizing substantial prey. The forelimbs remained fully transformed into flippers, broad enough to guide direction with precision while remaining relatively modest beside the tremendous length of the body. Near the rear, however, another feature interrupted every expectation: small hind limbs projected externally beside the tail region. They contained recognizable thigh bones, lower leg bones, ankle structures, and even the bones of tiny feet. These appendages belonged to an animal that spent its entire existence in open water, yet fragments of its distant terrestrial ancestry still accompanied every movement. Behind them extended the tail, ending in horizontal flukes, much like those carried by living whales. Their presence confirms that propulsion depended upon an upward and downward motion rather than the side-to-side sweep used by fishes. Even so, the immense body supporting those flukes remained unlike anything swimming today. Long before the tail completed each stroke, the rest of the animal already occupied an entirely different geometry, stretched into a living ribbon of muscle and bone. Seen as a whole, Basilosaurus combined a crocodile-like head with the length of a school bus, wrapped around a body far slimmer than its size suggested. It drifted through the Eocene seas with a silhouette that defied every modern expectation, revealing an evolutionary experiment that pursued predatory perfection through a design the oceans would never produce again. The most revealing part of Basilosaurus was not its immense length or its unusual silhouette, but the intricate arrangement hidden inside its jaws. Every bone of the skull supported a feeding system refined through countless generations, yet the teeth carried the greatest share of that design. They transformed the head into something far more specialized than the grasping mouths of most living whales, revealing a predator whose method depended upon gripping, cutting, and breaking apart prey rather than swallowing it in a single motion. Unlike the simple rows of nearly identical teeth found in many modern toothed whales, Basilosaurus possessed what paleontologists describe as heterodont dentition. Different parts of the jaw carried different kinds of teeth, each shaped for a distinct mechanical task. The mouth functioned less like a single tool and more like a carefully organized sequence, with every position contributing to the process of capturing and processing large animals. At the front of the jaws stood pointed incisors and forward premolars. Their crowns curved gently backward, forming natural hooks that resisted escape once they penetrated flesh. Instead of slicing immediately, these forward teeth excelled at securing movement. Any struggling prey attempting to pull away would force itself more firmly against the backward-facing curves, increasing the grip rather than weakening it. This arrangement reduced the chance of losing valuable prey during the first moments of contact, when resistance was strongest and every movement mattered. Farther behind, the architecture changed dramatically. The rear premolars and the remaining molar region broadened into laterally compressed teeth with sharply defined triangular crowns. Their edges bore fine serrations along both the forward and rear margins, producing cutting surfaces unlike the smooth cones carried by most living cetaceans. Each tooth complemented its opposite partner in the other jaw, allowing the upper and lower rows to meet with remarkable precision whenever the mouth closed. That meeting transformed the bite into a powerful shearing mechanism. Instead of merely puncturing flesh, the closing jaws pressed opposing serrated edges together in a coordinated motion capable of slicing muscle while simultaneously crushing resistant material beneath enormous pressure. Bone and tissue encountered the same relentless action, processed together through repeated bites rather than swallowed intact. The mouth therefore operated as a complete mechanical sequence. The front secured the victim. The rear completed the destruction. Individual rear teeth reached lengths approaching 10 centimeters, which is about 4 inches. Their size alone drew attention long before their purpose became fully understood. Early fossil collectors recovering isolated specimens from ancient sediments in Alabama occasionally regarded them as carved objects or unusually shaped tools, their polished surfaces seeming almost too regular to belong to a natural animal. Only careful anatomical study revealed their true place within one of the most formidable jaws ever assembled by a marine mammal. The teeth also carried a detailed record of their own history. Their surfaces displayed extensive wear with polished facets, chipped edges, and patterns of abrasion accumulated through years of repeated use. Such evidence reflects frequent encounters with large, resistant prey rather than occasional feeding upon soft-bodied animals. Every scratch and fracture became another small chapter preserved within enamel that survived long after the surrounding tissues disappeared. The skull reinforces this picture. Broad attachment areas for massive jaw muscles indicate exceptional closing strength, placing Basilosaurus among the most forceful biting cetaceans presently known from the fossil record. Its jaws lacked the streamlined swallowing strategy seen in dolphins and many other toothed whales. Instead, they opened, gripped, repositioned, and closed repeatedly, reducing prey into manageable portions before consumption. Every feature, from the backward curved front teeth to the interlocking serrated rear dentition, belonged to a predator built for sustained mechanical power, one whose feeding anatomy reveals deliberate specialization rather than simple, opportunistic feeding. Long after muscles dissolved and skin returned to the sea, another record remained. Bone preserved the final moments with remarkable fidelity, carrying impressions that no living witness could have described. Among the most valuable discoveries connected to Basilosaurus are not its own skeletons alone, but the damaged remains of the animals that crossed its path. Those injuries transformed ancient victims into enduring testimony, preserving patterns of predation with unusual clarity across millions of years. Some of the strongest evidence comes from the remarkable fossil beds of Wadi al-Hitan in Egypt, a landscape that was once part of the warm Eocene Sea. Within these sediments, paleontologists have uncovered numerous skulls belonging to Dorodon, a smaller early whale that shared the same waters with Basilosaurus. Many of these specimens belonged to young individuals whose bones had not yet reached full maturity. Instead of remaining untouched by time, their skulls carried deep punctures, fractured surfaces, and unmistakable impressions left by powerful teeth. Careful measurement revealed an extraordinary correspondence. The spacing between puncture marks matched the arrangement of Basilosaurus teeth with striking precision. Their depth reflected the force expected from an animal of immense size, while delicate serrated traces carved into the fossilized bone mirrored the cutting edges preserved on Basilosaurus rear teeth. Each damaged skull became another point of comparison, and together they formed a consistent anatomical pattern rather than a collection of isolated accidents. The position of those wounds proved equally revealing. They clustered around the skull and the elongated snout rather than appearing randomly across the skeleton. Such placement reflects deliberate targeting of the head, where injury could rapidly disable movement, disrupt the senses, or end resistance altogether. This distribution differs from the scattered damage expected if an animal simply seized whatever part of its prey happened to be within reach. Instead, the injuries reveal repeated precision directed toward the most vulnerable region of the body. Several specimens preserve evidence of more than one strike. Distinct groups of tooth impressions overlap or intersect, showing that the predator did not merely bite once before releasing its victim. The sequence preserved in bone suggests repeated contact, gripping firmly, adjusting position, then closing the jaws again. Every additional mark records another movement within an encounter that ended before the sea floor slowly buried both hunter and prey beneath accumulating sediment. The victims themselves tell another important part of the story. Bone density, skull proportions, and stages of skeletal development consistently identify these Dorodon individuals as juveniles rather than adults. Young whales represented the most vulnerable members of their populations, possessing smaller bodies, less experience, and fewer physical defenses. Basilosaurus appears to have recognized this imbalance, concentrating its efforts where the greatest return required the least expenditure of energy. Such selectivity reflects behavior shaped by evolutionary efficiency rather than indiscriminate feeding. Modern killer whales display a broadly comparable strategy when pursuing the calves of much larger whale species, separating young animals from protective adults before delivering decisive attacks. Basilosaurus achieved a remarkably similar outcome many millions of years earlier, directed toward distant relatives occupying the same ancient sea. The resemblance illustrates how similar ecological pressures can encourage comparable hunting solutions across vastly separated chapters of evolutionary history. Evidence from associated fossil deposits broadens this picture still further. Remains of rays, sharks, and large bony fishes have been recovered alongside Basilosaurus specimens, indicating a predator willing to exploit many different food sources whenever opportunity appeared. Yet the damaged Dorodon skulls remain uniquely informative because they preserve not merely the identity of prey, but the method by which that prey was overcome. Few extinct predators leave behind such direct anatomical testimony. In this ancient sea, bone itself retained the memory of pursuit, impact, repeated bites, and the practiced precision of an apex hunter whose behavior can still be traced through the marks it impressed upon another living skeleton. Among the many abilities that define living-toothed whales, one stands apart as an extraordinary achievement of evolution. The ocean carries sound across immense distances, and modern hunters have learned to shape that property into an intricate sensory language. Rather than depending entirely upon sight, they fill the surrounding water with rapid bursts of sound, receiving returning echoes that reveal the size, distance, movement, and texture of objects hidden beyond vision. For these animals, the sea becomes an ever-changing landscape painted with reflected sound instead of light. Sperm whales carry this remarkable ability into profound depths, descending more than 2,000 meters, that is nearly 1,243 miles, beneath the surface, while locating prey in complete darkness. Dolphins employ the same biological system with astonishing precision, detecting fish scarcely larger than a human finger from distances approaching 100 meters. Their foreheads contain a specialized organ composed of fatty tissue, commonly known as the melon, which focuses outgoing sound into highly directed beams. Returning echoes travel through equally specialized tissues of the lower jaw before reaching portions of the brain dedicated to interpreting this complex acoustic information. Nothing within the fossil anatomy of Basilosaurus suggests possession of this remarkable biological instrument. Detailed imaging of preserved skulls, together with careful anatomical comparison, reveals no evidence for the enlarged fatty forehead structure characteristic of echolocating whales. The specialized lower jaw adaptations responsible for receiving reflected sound are likewise absent. Internal features associated with processing sophisticated acoustic signals never appear within the preserved architecture of the skull. The anatomical foundations required for biological sonar had simply not yet evolved. Basilosaurus belonged to an earlier chapter in cetacean history, existing before the evolutionary transformation that eventually reshaped toothed whales into masters of underwater acoustics. It occupied oceans where another combination of senses proved entirely sufficient. Rather than constructing an invisible map through echoes, it encountered its surroundings by relying upon environmental conditions that favored different forms of perception. Vision almost certainly played an important role. The size and orientation of the eye sockets indicate well-developed eyes suited to a marine predator inhabiting the illuminated upper layers of the sea. Unlike modern deep-diving whales that routinely enter perpetual darkness, Basilosaurus spent much of its existence within waters reached by abundant sunlight. Shapes remained visible across considerable distances, allowing movement, pursuit, and recognition without depending upon acoustic reconstruction. Hearing still mattered, although in a different form. Instead of interpreting complex reflected signals, Basilosaurus likely detected broad pressure changes and low-frequency vibrations transmitted through water and conducted into the skull and jaws. Every large swimming animal displaced enormous volumes of surrounding water, creating waves of pressure that traveled outward in expanding patterns. Such disturbances offered valuable information regarding direction, movement, and approximate size, even without the detailed precision available to later echolocating whales. Some researchers compare this sensitivity to the function performed by the lateral line system in fishes, although mammals evolved through a different anatomical pathway. Basilosaurus appears to have combined ordinary hearing with exceptional awareness of water movement, producing an effective sensory strategy tailored to its own environment. It did not require perfect acoustic images because its world supplied abundant visual information alongside constant physical signals generated by the movements of nearby animals. Its preferred hunting grounds completed this sensory picture. Broad continental shelves remained comparatively shallow, their clear waters illuminated through much of the water column. Visibility extended far beyond what would be possible in the great depths explored by many modern cetaceans. Within such habitats, prey could neither disappear into endless darkness nor rely upon deep water to escape detection. Every movement disturbed the surrounding sea. Every passing body altered pressure within the water, and every beam of sunlight carried another outline across the ancient ocean. Basilosaurus belonged completely to that luminous world, succeeding through senses perfectly matched to an environment that no longer exists. Movement leaves no direct fossil behind. Muscle fades, tendons vanish, and the flowing rhythm that once carried an animal through water disappears long before stone begins preserving bone. What remains are the proportions of the skeleton, the surfaces where muscles once attached, and the subtle engineering locked inside every vertebra. From these enduring clues, paleontologists have gradually reconstructed the remarkable manner in which Basilosaurus crossed the Eocene Sea, revealing a style of locomotion unlike that of any living whale. Modern great whales travel through the ocean with bodies that remain comparatively rigid during each powerful stroke of the tail. Horizontal flukes rise and fall in broad, deliberate movements, while the spine flexes only where necessary to transfer muscular force efficiently toward the rear. This arrangement conserves energy over immense journeys, allowing many species to migrate across entire ocean basins with extraordinary endurance. Their bodies resemble living beams, channeling force toward the tail with remarkable mechanical economy. Basilosaurus inherited the same horizontal tail flukes, yet the rest of its anatomy tells a very different story. The elongated vertebrae that formed much of its body created a spine far more flexible than that of modern whales. Their internal structure, reduced in density by fluid-filled spaces, sacrificed some of the stiffness required for highly efficient long-distance propulsion. Rather than resisting bending, the body appears to have welcomed it, allowing movement to travel along much of its extraordinary length. Instead of concentrating motion primarily near the tail, Basilosaurus almost certainly generated a traveling wave that passed from behind the head through the trunk before reaching the flukes. The entire animal participated in propulsion. Each section of the spine contributed to the next, producing an undulating sequence more reminiscent of a giant eel or an immense sea snake than any whale alive today. The tail still supplied thrust, yet it worked in partnership with a body already flowing through continuous curves. The resulting silhouette would have been unlike anything familiar in the modern ocean. Nearly 18 meters in length, which is about 59 feet, the animal advanced through broad, sweeping waves that traveled from one end of its body to the other. Rather than presenting a single powerful tail stroke followed by a rigid glide, Basilosaurus carried its motion throughout nearly its entire frame, each bend preparing the next in an uninterrupted progression of muscular force. Such movement probably came with trade-offs. A highly flexible body generally sacrifices some efficiency during prolonged travel because energy is continually distributed across many moving segments instead of being concentrated through a rigid framework. This suggests that Basilosaurus may not have undertaken the vast seasonal migrations characteristic of several living baleen whales. Its anatomy instead appears better suited to remaining within productive warm seas, where abundant prey reduce the need for journeys across great distances. What it surrendered in endurance, it may have regained through agility. An elongated, flexible body possesses remarkable freedom to redirect momentum, weaving through changing paths with graceful precision. During pursuit, rapid turns and swift changes in orientation could be achieved without relying entirely upon the tail. The body itself became an active steering surface, bending smoothly around shifting currents and evasive prey. Its lightweight vertebrae contributed additional advantages. Reduced skeletal mass influenced buoyancy and likely improved acceleration despite the animal's impressive length. Every movement required less effort than a comparably sized body built from heavier bone, allowing the enormous predator to remain surprisingly responsive within the water. The small hind limbs contributed almost nothing to propulsion. Their position and limited size prevented meaningful participation in swimming, although they may have offered slight assistance during tight turns or while maintaining contact with struggling prey. Their greatest significance belonged to evolutionary history rather than mechanics. No living marine animal combines these anatomical features into the same pattern of movement. The flowing progression of a warm-blooded predator, propelled by a full-body undulation, vanished with Basilosaurus itself, leaving behind only the stone record from which that forgotten rhythm can now be imagined. An apex predator usually belongs to a particular coastline, an isolated sea, or a familiar stretch of ocean where conditions favor its survival. Basilosaurus belonged to something far larger. Its fossil record reveals an animal that spread across nearly every major marine environment of the Eocene, occupying a planetary range unmatched by any other large ocean predator known from the history of vertebrate life. Instead of ruling a single basin, it extended across an interconnected world of warm seas that no longer exists. Its remains have been recovered from North America, South America, Europe, North Africa, East Africa, the Middle East, South Asia, and New Zealand. Every continent preserving exposed marine rocks from the Eocene has yielded evidence of its presence, with Antarctica standing as the only notable exception. This remarkable distribution reflects more than fortunate fossil preservation. It reveals an animal capable of thriving across an immense variety of coastal environments while remaining firmly established at the highest level of the marine food web. North America provided the earliest discoveries and continues to produce some of the richest collections. Ancient marine deposits along the Gulf Coast, especially within Alabama, Mississippi, and Louisiana, have yielded hundreds of Basilosaurus specimens over nearly 2 centuries of excavation. So numerous were some of the enormous vertebrae that early settlers reportedly incorporated them into ordinary household uses before their scientific significance became widely understood. Bones that once formed the backbone of a global predator briefly entered everyday human life, their true history remaining hidden beneath ordinary familiarity. Far across the ancient Tethys Sea, another extraordinary archive rests within the Egyptian desert. Wadi al-Hitan preserves what was once a warm seafloor, teeming with marine life. More than 1,000 fossil cetaceans have been recovered from these sediments, including dozens of Basilosaurus skeletons preserved in remarkable completeness. Entire bodies settled gently into soft sediment, allowing vertebrae, ribs, skulls, and even delicate hind limb bones to remain associated through millions of years of burial before emerging once again beneath the desert sun. Europe adds another chapter to this extraordinary range. Fossils recovered from England, Belgium, and Italy demonstrate that Basilosaurus occupied the northern margins of the Tethys Sea, swimming through waters that would one day become the English Channel and the North Sea. At the opposite end of that immense tropical ocean, discoveries from Pakistan and India reveal its presence within eastern marine habitats connected to the developing Indo-Pacific region. The predator ranged freely across waters separated today by thousands of kilometers, which is about 1,864 miles, yet united during the Eocene by broad, uninterrupted seas. Material recovered from New Zealand extends this picture even farther. Fossils from the southern hemisphere confirm that Basilosaurus entered the ancient Pacific basin, demonstrating that its remarkable distribution crossed hemispheres rather than remaining confined to northern tropical waters. Few marine predators have ever established themselves so broadly while maintaining comparable size and ecological dominance across such distant environments. This worldwide occupation becomes even more striking when compared with familiar modern hunters. Great white sharks, despite their formidable reputation, remain absent from extensive regions of today's oceans. They rarely inhabit the warmest equatorial waters for prolonged periods, seldom occupy the highest latitudes, and avoid many parts of the deepest tropical seas. Their range, impressive though it is, contains clear geographic boundaries shaped by modern climate and ocean circulation. Basilosaurus encountered far fewer such limitations. The connected warm oceans of the Eocene permitted a single body plan to spread across productive marine ecosystems almost without interruption. Similar environmental conditions extended from one continental margin to the next, allowing populations to occupy habitats linked by broad tropical corridors rather than isolated by cold barriers. Across this continuous marine world, the same elongated predator repeatedly appeared, leaving its skeleton behind wherever ancient seas eventually became stone. Measured by the breadth of its distribution, no later marine predator has matched the reach achieved by Basilosaurus. Its reign stretched not merely across oceans, but across an entire planetary seascape shaped by conditions that have never returned. Beneath every successful predator lies a far older story, one written not in triumph, but in gradual change. Long before Basilosaurus ruled the warm seas, its ancestors still carried the shape of the land upon their backs. Their feet pressed into damp ground beside the ancient Tethys Sea, where rivers met broad coastal waters across landscapes that would one day become parts of Pakistan and northern India. There, about 53 million years ago, lived Pakicetus, a modest mammal whose future could not have been guessed from its appearance alone. Its body was built more like a wolf than a whale, with sturdy limbs, weight carried over its feet, and senses adapted for a terrestrial world. It hunted along the margins where land dissolved into shallow water, crossing between both environments with ease. The chemistry preserved inside its teeth tells an equally revealing story. Oxygen isotope ratios within the enamel show that Pakicetus drank fresh water, confirming that it remained fundamentally a land animal even while spending part of its life beside rivers and coastal channels. The great transformation had begun, yet it was still taking its earliest steps. Across the following millions of years, the fossil record preserves an unusually complete sequence of forms, each carrying slightly more of the ocean within its anatomy. Ambulocetus appeared by about 49 million years ago, larger and more comfortable in the water, though still capable of walking upon land. Its limbs remained powerful enough for movement across shorelines, while its broad body hinted that swimming was becoming an increasingly important part of daily life. It belonged to both worlds, though the balance had already begun to shift. Soon afterward came Rhodhocetus, living roughly 47 million years ago. Its outline had become noticeably more streamlined, reducing resistance as it passed through warm coastal seas. The hind limbs had diminished, making movement across dry ground increasingly awkward and inefficient. Every generation carried slightly stronger adaptations for marine life, while the ability to return permanently to land slipped further beyond reach. The path toward the open ocean had become a one-way journey. Protocetus and several closely related forms carried that commitment even farther. They lived entirely within marine environments, giving birth, feeding, and traveling without returning to shore. Small external hind limbs still remained, preserving a visible reminder of distant ancestors, yet they could no longer support the body's weight on land. Evolution had not erased the past all at once. Instead, it left fading signatures that lingered while new structures assumed greater importance. Then emerged Basilosaurus, stretching nearly 18 meters, which is about 59 miles of, no, stretching nearly 18 meters, which is about 59 feet. Rather, stretching nearly 18 meters, that is nearly 59 feet in length, fully committed to life in the sea and occupying the highest level of the marine food web. Within only about 15 million years, an animal descended from a shoreline mammal had become one of the dominant predators on Earth. Measured against geological history, this interval was astonishingly brief. Dinosaurs endured for roughly 165 million years, while recognizable sharks have persisted for more than 400 million years. Yet the rise from Pakicetus to Basilosaurus unfolded within only a small fraction of those immense spans. The reason lay not in purpose or ambition, but in opportunity. The Eocene seas were warm, richly productive, and remarkably free of large mammalian competitors occupying the highest predatory role. Countless ecological possibilities remained available for any lineage capable of exploiting them. Natural selection rewarded every improvement that allowed deeper swimming, stronger hunting, greater endurance, and more efficient movement through marine habitats. Generation after generation, those small advantages accumulated until the shoreline hunter had become something entirely transformed. Evolution did not hurry because it possessed intent. It advanced because an open place existed at the summit of the ancient ocean, and the fossil record preserves, with uncommon clarity, the remarkable speed at which life rose to fill it. Among all the bones recovered from Basilosaurus, none seem more revealing than the small limbs carried near the end of its body. They attract attention not because they are imposing, but because they preserve a remarkable instant in evolutionary history, a moment when the past had not yet disappeared and the future had not yet fully arrived. They are evidence that transformation does not always erase what came before in a single sweep. Sometimes it leaves traces behind, suspended between two worlds. The rear limbs of Basilosaurus had already become dramatically smaller than those of its distant ancestors. Compared with Pachycetus or Ambulocetus, whose hind legs remained fully capable of supporting the body across land, these appendages had shrunk into structures with an entirely different role. Yet they had not vanished. They projected slightly from the body's surface, remaining visible to the outside world rather than retreating beneath skin and muscle. Their presence reminds us that evolution often proceeds through countless, small revisions rather than sudden replacement. Fossils recovered from Egypt preserve these limbs in extraordinary completeness. Paleontologists have identified a femur, the great bone of the upper leg, along with the tibia and fibula of the lower leg. Beyond them lie metatarsals and even delicate phalanges, the bones that once formed toes. Every major component of a recognizable leg remained present. Looking across the assembled skeleton, there is no uncertainty about what these bones represent. They belong to feet that trace their ancestry to mammals that had once walked confidently across solid ground. Even more remarkable is the condition of the joints themselves. The knee retained the ability to bend, while the ankle could still flex through a limited range of movement. These were not fused remnants locked forever into a rigid position. They remained genuine limbs with movable connections between their bones. Even so, their usefulness had changed almost beyond recognition. They were far too small to reach the ground beneath an animal of such immense proportions. They also occupied a position that prevented them from contributing meaningful thrust during swimming. Neither land nor sea offered them a practical role in locomotion. The explanation favored by many researchers reaches beyond movement and instead turns toward reproduction. During mating in open water, maintaining stable contact between two enormous marine mammals presents considerable mechanical challenges. Small movable hind limbs may have acted as anchoring structures, helping partners remain aligned during the process. Although certainty remains beyond reach, this interpretation agrees well with the anatomy preserved in the fossils. Additional support comes from comparisons among different Basilosaurus skeletons. Individuals interpreted as males, based upon overall proportions and other anatomical differences, often possess hind limbs that appear somewhat larger and more robust than those of presumed females. Such variation is consistent with structures shaped partly through sexual selection, where reproductive success influences anatomy even after a feature has lost its original purpose. Perhaps the deepest significance of these limbs lies not in what they accomplished, but in what they revealed about inheritance itself. The ancient genetic instructions responsible for producing legs had not yet fallen completely dormant. They continued expressing themselves, though in a far more limited form than they once had. Millions of years after the lineage became fully marine, those developmental pathways still echoed through each new generation, leaving behind external reminders of a terrestrial ancestry that stretched deep into the past. Later whales completed the transformation. Their hind limbs withdrew beneath the body, shrinking into small pelvic fragments, disconnected from the main skeleton and hidden beneath muscle. Those bones still exist inside living whales today, carrying almost no practical function and no outward expression. Basilosaurus stands at the threshold between those distant chapters, preserving upon its own body an evolutionary story still unfolding, where the final footsteps of life on land had not yet entirely faded beneath the waves. A successful design rarely appears only once. When an environment consistently rewards the same strengths, evolution often arrives at remarkably similar answers across distant places. Basilosaurus was not a solitary marvel confined to one stretch of ancient shoreline. It belonged to a broader lineage that spread across the warm connected seas of the Eocene, producing multiple species that shared the same commanding role while adapting to different corners of a single global ocean. The best known of these is Basilosaurus setoides, discovered within marine deposits stretching across what is now Alabama, Mississippi, and Louisiana. These fossils formed the foundation of nearly 2 centuries of scientific study, beginning with some of the earliest discoveries that puzzled naturalists before the true identity of the animal became clear. Hundreds of specimens have since emerged from these sediments, preserving skulls, vertebrae, ribs, and countless other bones. Together, they have created the most detailed portrait available of one of the greatest marine predators the planet has ever produced. Far across the ancient sea, another closely related species occupied a different world while fulfilling much the same ecological role. Basilosaurus isis lived within the waters that covered what is now Egypt, particularly across the remarkable fossil beds of Wadi al-Hitan. During the Eocene, this landscape rested beneath the broad expanse of the ancient Tethys Sea, where warm shelf waters supported abundant marine life. Although unmistakably a Basilosaurus, this species displays subtle differences in the proportions of its skull and vertebrae, reflecting the distinct environmental conditions and prey communities that shaped its evolution. Despite those regional differences, both species reached strikingly similar overall body lengths, approaching 18 meters, which is about 59 feet. This shared scale was almost certainly no coincidence. The warm, shallow seas of the Eocene imposed their own ecological boundaries upon the largest hunters. A predator too small would struggle to dominate large prey, while one growing substantially larger would demand increasing amounts of food from an ecosystem with practical limits. Across opposite margins of the ancient ocean, natural selection guided separate populations toward nearly the same physical dimensions because those dimensions represented an effective balance between strength, mobility, and the resources available within their environments. Evidence recovered from Europe, South Asia, and the Southern Hemisphere hints that the story extends even farther. Fossils assigned to Basilosaurus, or to very closely related members of its family, suggest additional regional diversity that remains only partly understood. Many specimens are fragmentary, preserving isolated vertebrae, teeth, or sections of skull that offer tantalizing glimpses without revealing the complete picture. Each new discovery adds another piece to an expanding map of evolutionary variation spread across an interconnected planetary sea. Basilosaurus also shared those waters with other members of the same broader family. Predatory early whales, such as Syntheocetus and Masracetus, occupied neighboring positions within the marine food web, carrying elongated bodies and fully aquatic lifestyles of their own. They were formidable animals in their own right, yet Basilosaurus consistently stood among the largest representatives known from this remarkable lineage. Exactly how these predators divided their resources remains uncertain. Different hunting grounds, preferred prey, or feeding strategies may have reduced direct competition, but the fossil record has not yet preserved enough evidence to resolve those relationships with confidence. Some questions remain suspended between scattered bones and vanished coastlines, waiting for discoveries still buried beneath ancient sediments. Even with those uncertainties, one conclusion emerges with unusual clarity. The Basilosaurus body plan was not an isolated curiosity confined to a single shoreline or a brief evolutionary experiment. It appeared across multiple marine provinces, persisted through immense connected seas, and proved successful under different environmental conditions. That repeated success reveals a design refined by the opportunities of the Eocene Ocean, one that rose again and again wherever warm waters offered the same path to supremacy. Some scientific names emerge from careful understanding. Others survive as lasting reminders that knowledge is built through correction as much as discovery. The name Basilosaurus belongs to the second kind. It carries within it one of the most enduring mistakes in the history of paleontology, preserved not because the error remained convincing, but because the rules of scientific naming demanded that it remain unchanged forever. The first bones appeared across the American South during the early decades of the 19th century. In what are now Alabama, Louisiana, and Mississippi, ancient marine sediments slowly surrendered enormous fossils that had rested beneath the ground since the Eocene. Weather and erosion exposed vertebrae broader than dinner plates, ribs thicker than a man's arm, and teeth whose edges resembled carefully crafted blades. Nothing living offered an obvious comparison. Anyone standing beside those remains would have struggled to imagine the creature from which they had come. When the American naturalist Richard Harlan examined the material during the year 1834, he reached a conclusion that seemed entirely reasonable according to the knowledge available at the time. The immense vertebrae and elongated body suggested an enormous marine reptile rather than a mammal. Ancient reptiles already occupied an important place in scientific thought, while fossil whales were almost unknown. Harlan believed he had uncovered the remains of a gigantic sea lizard, unlike anything previously described. He chose the name Basilosaurus, meaning king lizard. The description entered the scientific literature, satisfying the requirements for formal publication. At that moment, the name became permanently attached to the fossils, though the true nature of the animal had yet to be recognized. Only a few years later, the British anatomist Richard Owen carefully re-examined the same remains. The differences became unmistakable once the teeth received close attention. Reptilian teeth are generally simple in structure, but these possessed complex double roots characteristic of mammals. The skull displayed mammalian proportions, while the vertebrae and other bones supported the same conclusion. Piece by piece, the evidence converged upon an entirely different identity. This was not a marine reptile, it was an ancient whale. Recognizing the mistake, Owen proposed a replacement name, Zyglodon, meaning yolk tooth, inspired by the distinctive shape of the rear teeth. Unlike the misleading original, this new name accurately reflected one of the animal's most recognizable anatomical features. Under ordinary circumstances, such a correction might have seemed inevitable. Scientific naming, however, follows principles designed to preserve stability rather than perfection. According to the International Code of Zoological Nomenclature, the earliest properly published name generally retains permanent priority, even if later research demonstrates that the original interpretation was mistaken. Because Harlan had fulfilled the formal requirements first, Basilosaurus remained the official name. Accuracy yielded to consistency, ensuring that scientists across the world would continue referring to a whale by a title that described it as a lizard. The story acquired another remarkable chapter during the following decade. The American showman Phineas Taylor Barnum obtained reconstructed Basilosaurus material and transformed it into a spectacular public attraction. Duplicate bones were added to exaggerate the animal's length until the mounted skeleton approached 35 meters, which is about 115 feet. Displayed under the dramatic name Hydrarchos, it was presented as an immense sea serpent worthy of ancient legends. Vast audiences gathered to witness the astonishing creature, unaware that the reconstruction itself had been carefully enlarged for theatrical effect. The irony has endured ever since. Few animals represent mammalian evolution more completely than Basilosaurus, a warm-blooded, air-breathing whale that nourished its young with milk and spent its entire life in the sea. Yet the name attached to its bones still declares it to be a king lizard, preserving within every scientific paper and museum display a reminder that even science carries the lasting footprints of its earliest misunderstandings. Before any predator can reach extraordinary size, the world around it must first become capable of sustaining such an appetite. Long before Basilosaurus became the dominant hunter of warm seas, the ocean itself had entered an unusually generous chapter, one in which heat flowed through every level of life, strengthening the smallest organisms before ultimately supporting the largest. The climatic backdrop was the early Eocene climatic optimum, a prolonged interval stretching roughly from 53 million to 50 million years ago. Across the last 66 million years of Earth's history, no other sustained period has remained comparably warm. It exceeded the climates of the later Pleistocene ice ages, surpassed the warmth of the present interglacial, and stood beyond anything measured during the era of modern scientific observation. The planet functioned under conditions that have no direct modern counterpart. Much of that warmth reflected an atmosphere carrying unusually large amounts of carbon dioxide. Current scientific estimates place atmospheric concentrations during the warmest interval between 1,000 and 2,000 parts per million. Before widespread industrial activity, the atmosphere contained roughly 280 parts per million. Modern measurements remain near 420 parts per million, substantially below the estimated Eocene peak. The difference was expressed not only in the air above the oceans, but throughout the waters themselves. Near the equator, sea surface temperatures reached approximately 35 degrees Celsius, or 95 degrees Fahrenheit, warmer than any tropical ocean surface documented during the modern instrumental era. Even farther north, conditions would appear startling to present-day observers. The surface of the Arctic Ocean is estimated to have reached approximately 23 degrees Celsius or 73 degrees Fahrenheit, comparable to waters now associated with much lower latitudes during the warmer months of the year. Warmth on its own does not guarantee abundance, yet it profoundly shapes the speed at which biological systems operate. Microscopic plankton, drifting almost invisibly through the upper ocean, grow and reproduce more rapidly when temperatures remain favorable. Their expanding populations provide nourishment for immense numbers of small fish. Those fish sustain larger hunters, which in turn support still greater predators. Energy passes upward through the food web with remarkable efficiency whenever the foundation is exceptionally productive. Across broad continental shelves, flooded by elevated sea levels, sunlight reached the seafloor over immense distances, encouraging thriving communities that stretched across landscapes now transformed into mountains, deserts, and dry plains. Every layer of this ancient marine world contributed to an ecosystem of unusual richness. Rather than isolated pockets of productivity, entire ocean basins became linked through warm, connected waters capable of sustaining remarkably dense concentrations of life. The consequence was an ocean carrying more prey across each square kilometer than modern tropical seas generally support. Small fish multiplied in extraordinary numbers. Larger fishes flourished above them. Marine reptiles had already disappeared, leaving opportunities that mammals were beginning to occupy with increasing success. Every successful hunt returned energy to a predator capable of growing larger, surviving longer, and producing offspring that inherited the same advantages. Within this remarkably productive system, Basilosaurus represented the highest expression of what the environment could sustain. Its immense body, worldwide distribution, and the abundance of fossils recovered from ancient shorelines all point toward ecosystems rich enough to nourish large populations of a predator approaching 18 meters, which is about 59 miles in error? No. Better expressed as 18 meters without conversion, because only kilometers and feet require accompanying conversions under our narrative rules. Such an animal could not have persisted across multiple ocean basins without an equally extraordinary foundation beneath it. Yet, climates never remained fixed forever. Through the later Eocene, global temperatures gradually declined as volcanic outgassing diminished and patterns of ocean circulation slowly shifted. The immense heat engine that had powered this flourishing marine world began losing strength, and the living networks built upon that warmth would eventually be asked to adapt to a very different sea. Maps of the modern world offer little preparation for the ocean that carried Basilosaurus. Familiar coastlines had not yet taken shape. Continents remained in motion, and broad expanses of warm sea covered regions that today lie beneath deserts, mountain ranges, and fertile plains. The geography surrounding this predator was not merely an earlier version of the present. It belonged to a planetary arrangement that has vanished almost completely. At the heart of that vanished world stretched the Tethys Sea, an immense tropical waterway extending across lands now recognized as the Middle East, Southern Europe, Turkey, Iran, and much of Central Asia. Rather than isolated basins separated by narrow passages, the ancient ocean formed a broad equatorial connection between the developing Atlantic and the waters that would eventually become the Indian and Pacific Oceans. Its extensive shallows absorbed sunlight across enormous distances, creating marine environments unlike any existing today. For Basilosaurus, this sea provided one of the richest hunting grounds on Earth. Vast continental shelves lay beneath warm, illuminated water where marine life flourished in exceptional abundance. Fish, early whales, sharks, rays, and countless smaller organisms occupied habitats linked together across thousands of kilometers, which is about 1,864 miles. Instead of scattered feeding grounds separated by colder barriers, productive ecosystems blended into one another with remarkable continuity, allowing a large predator to range across immense areas without leaving favorable conditions behind. Yet the Tethys Sea existed only because Earth's continents occupied temporary positions. The African landmass continued drifting northward toward Eurasia. As those immense plates slowly converged, shorelines shifted, shallow seas narrowed, and marine corridors gradually disappeared. The process unfolded across millions of years, almost imperceptible within a single lifetime, yet relentless when measured against geological time. The environment that had sustained generations of marine predators slowly began surrendering its defining character. Far to the south, another change of enormous consequence remained underway. The passage separating the southern end of South America from the Antarctic Peninsula was either closed or only partly open. Without a complete connection, the powerful current that now circles Antarctica could not yet develop into its modern form. Cold polar water, therefore, remained far less effective at spreading throughout the world's oceans, allowing warmth to persist across a much broader range of latitudes than it does today. Because this global circulation pattern had not fully emerged, the contrast between tropical and polar waters remained much weaker. Deep oceans retained more heat, and marine animals adapted to warm conditions occupied regions that would later become too cold for them. Basilosaurus belonged to an ocean whose thermal character remained comparatively even from lower to higher latitudes, permitting an ecological reach that later marine predators would never experience under cooler global conditions. The Atlantic Ocean also presented a different face. South America and Africa still rested closer together than they do today, influencing currents, coastlines, and the movement of nutrients through the expanding basin. Across much of the world, sea level stood between 50 and 100 meters higher than the present day, which is about 164 feet and 328 feet. Those elevations flooded enormous stretches of low-lying continental crust, producing broad coastal shelves where sunlight, warmth, and abundant life combined in enduring harmony. Some of the most celebrated fossils of Basilosaurus reveal this transformation with striking clarity. The skeletons preserved at Wadi al-Hitan now rest deep within an Egyptian desert. Approximately 150 kilometers, that is nearly 93 miles, from the nearest shoreline. When those animals lived, the same ground formed part of a shallow tropical seafloor washed by waves beneath an open sky. Even while Basilosaurus flourished, the foundations of its world were already changing. India continued its collision with Asia. Africa pressed steadily toward Europe, and southern ocean gateways widened little by little. The geography supporting this remarkable predator was never permanent, only a passing arrangement in Earth's endlessly shifting design. Among living whales, the body tells only part of the story. Much of their success resides inside the skull, where large and highly specialized brains support social bonds that can endure for decades. Hunting traditions passed from one generation to the next, and vocal exchanges that travel across vast expanses of open water. In many modern species, survival depends as much upon shared knowledge as physical strength. Basilosaurus belonged to a very different chapter, one in which dominance rested upon another foundation entirely. Its brain was not primitive in the sense of being poorly adapted, but it differed profoundly from that of modern whales. Paleontologists estimate its encephalization quotient, the standard measurement comparing expected brain size with body mass, to have been substantially lower than that of living dolphins or toothed whales. Modern bottlenose dolphins possess one of the highest encephalization quotient values among all animals outside humanity, reflecting remarkable cognitive flexibility. Basilosaurus occupied a far more modest position, with proportions resembling those of much earlier mammals, rather than the sophisticated marine descendants that would appear millions of years later. This conclusion does not depend upon size alone. Fossil skulls preserve the internal shape of the brain case well enough for researchers to reconstruct endocasts, natural impressions revealing the relative proportions of different brain regions. Those reconstructions indicate comparatively limited expansion of the neocortex, the outer region associated in modern mammals with advanced learning, planning, social behavior, and flexible problem solving. The essential machinery for controlling movement, sensation, and instinct remained fully capable, yet the architecture supporting highly elaborate cognition had not reached the form familiar in living whales. The contrast extends beyond the brain itself. Modern toothed whales possess specialized structures dedicated to producing and receiving precisely controlled sound. Their foreheads contain the fatty organ responsible for directing acoustic signals, while equally specialized tissues within the lower jaw receive returning echoes that the nervous system transforms into detailed representations of the surrounding world. Basilosaurus lacked these defining adaptations. Its skull reveals no evidence for the anatomical structures required to generate sophisticated biosonar, nor the neural organization expected for processing complex streams of returning acoustic information. Without those capabilities, there is little reason to imagine rich acoustic societies resembling those of present-day dolphins, sperm whales, or hunting groups of killer whales. Equally revealing is the fossil evidence itself. Repeated discoveries of juvenile prey bearing characteristic bite marks suggest attacks carried out by a single powerful hunter rather than coordinated groups surrounding vulnerable animals from multiple directions. No known fossil assemblage indicates organized pods traveling, feeding, or defending one another through coordinated behavior. Every available clue points toward an animal that spent much of its existence alone. Such solitude did not represent a weakness within the Eocene seas. It reflected the ecological conditions of the age. In an ocean overflowing with prey and lacking competitors of comparable scale, there was little evolutionary pressure favoring cooperation. Success belonged to whichever body plan captured food most efficiently, survived to reproduce, and passed those traits onward through countless generations. The result was an apex predator assembled less through expanding intelligence than through relentless refinement of physical design. A long, flexible body carried formidable muscles through warm coastal waters. Powerful jaws combined grasping teeth at the front with interlocking cutting teeth farther back. Acute senses suited the illuminated shallows where prey remained plentiful. Millions of years of natural selection polished these features until they worked together with remarkable effectiveness. For approximately 15 million years, that combination proved entirely sufficient. Basilosaurus did not inherit the complex societies, cultural traditions, or elaborate communication systems that define modern whales. It ruled through anatomy, instinct, and an environment perfectly matched to both, demonstrating that, for a long interval in Earth's history, extraordinary intelligence was not the only path to supreme dominance. No ruler exists without a kingdom, and the realm inhabited by Basilosaurus bore little resemblance to the oceans familiar today. It drifted with creatures that flourished for millions of years before vanishing almost completely from the history of life. Their fossils remain scattered through ancient seabeds, preserving the memory of an ecosystem assembled under conditions that no longer exist. To enter that sea is to encounter an entire caste whose stories ended long before the modern ocean took shape. Among the most abundant whales of that age was Dorudon, a close relative that shared the warm coastal waters with its much larger cousin. Far smaller, more streamlined, and built for swift travel through open water, Dorudon appears throughout fossil deposits in remarkable numbers. Entire skeletons, isolated skulls, and juvenile remains reveal an animal that likely hunted fish with agility rather than overwhelming force. Yet its abundance also made it one of the most frequent victims. Numerous juvenile skulls preserve unmistakable bite marks matching the jaws of Basilosaurus, preserving moments in which predator and prey briefly met before becoming part of the geological record together. Other hunters also patrolled these seas, although none occupied the highest position. Sharks belonging to the lineage that would eventually give rise to the colossal otodus Megalodon had already appeared, but they had not yet reached their later dimensions. During the Eocene, they remained capable predators, feeding upon fish and smaller marine animals, while occupying a level beneath the immense whale that dominated the coastal shelves. Their future greatness still lay millions of years ahead. Broad expanses of warm shallows also supported giant sea turtles. Some reached approximately 2 meters in shell length, that is nearly 6.6 miles, moving steadily through waters rich with seagrasses and drifting vegetation. Their impressive size offered protection against many predators, yet against an animal possessing the jaws and strength of Basilosaurus, even these ancient reptiles represented potential prey whenever opportunity favored the hunter. Sharing those same coastal habitats were primitive relatives of today's manatees and dugongs. These early sirenians grazed upon underwater meadows stretching across extensive continental shelves. Their lives revolved around feeding rather than speed, and their heavy bodies reflected that peaceful existence. Within an environment ruled by a massive carnivore, such herbivores formed another strand in the intricate web of energy flowing upward through the ecosystem. Beneath these larger animals swam schools of fishes unlike those inhabiting present seas. Entire evolutionary branches of large, bony fishes flourished during the Eocene before disappearing without leaving direct descendants. Although unfamiliar today, they provided nourishment for countless intermediate predators, which in turn sustained still larger hunters. Their disappearance reminds us that even successful lineages can fade completely, while the ocean quietly rebuilds itself around new forms. Far to the south, another remarkable inhabitant entered the scene. Fossils from what are now New Zealand and Antarctica revealed giant penguins approaching 1.5 meters in height, which is about 5 feet. These towering seabirds bore little resemblance to the smaller species recognized today. Their long beaks and powerful swimming abilities allowed them to exploit coastal waters that also fell within the range of Basilosaurus, creating encounters between predators and birds unlike anything witnessed in the modern world. Equally striking is what these ancient waters lacked. There were no great white sharks slicing through the surf, no killer whales hunting in coordinated family groups, no sperm whales descending into immense depths, no blue whales filtering enormous volumes of seawater, and none of the dominant tuna or many familiar bony fish families that define present oceans. Nearly every recognizable giant of today's marine world still belonged to the future. The Eocene Sea therefore stands apart as a vanished community rather than an earlier version of the present. Basilosaurus occupied its highest place, surrounded by companions, rivals, and prey whose lineages have mostly ended. Their world survives only through stone, inviting each fossil to speak for an ocean whose living voices have long since fallen away. Some places preserve bones, others preserve entire worlds. Among all the fossil localities ever uncovered, none has revealed the life of Basilosaurus with greater clarity than a broad expanse of weathered rock lying deep within the Egyptian Western Desert. Today it appears dry beyond measure, yet every layer beneath its surface records an age when warm tropical water stretched to every horizon. Known in Arabic as the Valley of the Whales, this remarkable landscape earned recognition as a World Heritage Site through the United Nations Educational, Scientific, and Cultural Organization during the year 2005. Its significance reaches far beyond the beauty of exposed fossils. The rocks beneath the desert were once soft sediments resting on the floor of a shallow branch of the ancient Tethys Sea. Accumulating grain by grain while Basilosaurus remained one of the dominant hunters gliding through those sunlit waters. As countless generations of marine creatures lived and died, their remains settled into the seabed. Gradually, those sediments thickened, compressed, and transformed into stone. Over immense spans of geological time, movements within Earth's crust lifted the ancient seabed above the surrounding landscape. Wind then carried away layer after layer until skeletons hidden for tens of millions of years slowly emerged from the surface. The desert did not create these fossils, it patiently uncovered them. The scale of preservation found across the Valley of the Whales remains almost unmatched. More than 1,000 fossil whales have been documented within the site, representing numerous species from the Eocene seas. Among them are dozens of Basilosaurus individuals, several preserved with extraordinary completeness. Vertebrae remain linked in their original sequence. Ribs curve naturally around the body cavity, and skulls still rest where they settled after death. Rather than isolated fragments collected from distant places, these skeletons preserve the final arrangement of entire animals. Even more remarkable is the company these whales continue to keep. Around the larger skeletons lie the remains of Dorodon, ancient rays, sharks, fishes, sea turtles, and primitive relatives of modern sea cows. Because they occupy the same layers of sediment, scientists can reconstruct relationships throughout the ecosystem instead of studying each species in isolation. Predator, prey, scavenger, and herbivore all remain together within a shared geological chapter, preserving a community instead of scattered memories. Many of the most celebrated Basilosaurus skeletons have never been removed from the stone that protected them. They remain partially exposed where visitors can walk beside them, following the length of vertebral columns extending across the desert floor. Standing beside these fossils reveals proportions impossible to appreciate from museum displays alone. Each skeleton rests exactly where the ancient sea surrendered it, allowing the surrounding landscape to become part of the story rather than merely its backdrop. The Valley of the Whales also yielded the most complete hind limb material ever discovered for Basilosaurus. Tiny femurs, lower leg bones, ankle elements, and delicate toe bones survived together with remarkable completeness. These fossils transformed long-standing speculation into direct anatomical evidence, revealing that the reduced limbs remained genuine legs rather than shapeless remnants hidden within the body. They became one of the clearest demonstrations of evolution preserved in stone. Perhaps the greatest impression left by this place arises not from any single fossil, but from the contrast surrounding them. The nearest coastline now lies approximately 150 kilometers away, which is about 93 miles. Dry valleys stretch beneath an intense sky, where shifting sand replaces rolling waves. Yet beneath every step rests the floor of a vanished tropical sea. Basilosaurus still lies within its final resting place, surrounded by companions from an ocean erased by time, while the desert above continues its patient work of revealing a world that never truly disappeared, only changed beyond immediate recognition. Some fossils reveal the shape of an animal, others reveal the pace at which evolution works. The reduced hind limbs of Basilosaurus belong to the second category, offering a rare glimpse into a transformation that had not yet reached its conclusion. They were more than anatomical curiosities. They were evidence that ancient genetic instructions could linger long after their original purpose had begun to fade. Earlier, those small external legs appeared as remnants of a terrestrial ancestry, but their deeper meaning extends far beyond the bones themselves. Every mammal develops according to an intricate sequence of genetic signals that determines where the head forms, where the spine extends, and where each limb emerges. Among the most influential participants in this process are the homeobox genes, master regulatory genes that organize the body plan of every vertebrate. They establish the position of limbs, guide their growth, and influence how each region develops throughout early embryonic life. In Basilosaurus, those ancient instructions had not disappeared. The genetic program responsible for building hind limbs still activated during development, just as it had in distant land-dwelling ancestors. The remarkable difference lay elsewhere. Rather than eliminating the instructions entirely, evolution had gradually altered the signals, controlling how strongly those instructions were expressed. Growth began normally, yet the process slowed before reaching completion. The result was a recognizable leg that never developed into a structure capable of supporting the body or driving movement through water. This gradual reduction illustrates one of evolution's most consistent patterns. Structures rarely vanish in a single step. They become progressively smaller across countless generations as natural selection favors individuals that devote less energy to producing tissue with little practical value. Every gram of bone, muscle, and blood requires resources to construct and maintain. When a structure contributes almost nothing to survival or reproduction, even modest reductions can offer slight advantages that accumulate over immense spans of time. Basilosaurus occupied a fascinating midpoint within that process. Its hind limbs still projected beyond the surface of the body. They retained distinct joints, recognizable long bones, and articulated toes. Although they no longer served locomotion, they had not yet retreated beneath the skin. They represented evolution during transition rather than before or after it, preserving an intermediate stage that later whales would no longer display. As succeeding whale lineages emerged during the following geological ages, the transformation continued. The hind limbs became even smaller until they disappeared from external view altogether. The pelvis separated from the vertebral column, losing its structural connection with the rest of the skeleton. What remained were isolated pelvic bones suspended within surrounding muscles, no longer supporting legs and no longer visible from outside the body. Their presence nevertheless testified that the developmental program responsible for producing hind limbs had never been erased completely. Every living whale carries these hidden pelvic remnants. Blue whales, sperm whales, killer whales, dolphins, porpoises, and river dolphins all possess small paired pelvic bones concealed within their bodies. Though their appearance differs among species, they descend from the same evolutionary pathway recorded so clearly in Basilosaurus. The genetic networks guiding their formation remain active, although their expression has been reduced to a fraction of what existed in distant ancestors. Because those developmental pathways continue to operate, Basilosaurus occupies an unusually meaningful position within evolutionary history. It preserves the visible stage between functional walking limbs and the concealed pelvic fragments carried by modern whales. The animal, therefore, represents more than an extinct predator from an ancient sea. It embodies a biological process unfolding across millions of years, demonstrating that evolution often proceeds through gradual adjustment rather than abrupt replacement. Within its modest hind limbs survives one of the clearest records of how inherited structures fade, persist, and continue to echo through every whale swimming in Earth's oceans today. For millions upon millions of years, the world that sustained Basilosaurus seemed remarkably stable. Warm seas stretched across broad continental shelves, sunlight reached expansive shallow waters, and life flourished through a food web dense enough to support one of the largest predators its age had ever produced. Yet, beneath that appearance of permanence, the planet itself continued to change, carrying within its restless geology the conditions that would eventually unravel an entire marine kingdom. The disappearance of Basilosaurus from the fossil record occurred approximately 34 million years ago, aligning with one of the clearest climatic turning points preserved anywhere in Earth's geological history. This interval, known as the Eocene-Oligocene transition, is recorded with remarkable consistency in ocean sediments recovered from distant parts of the world. Layers of microscopic shells, changes in stable oxygen isotope ratios, and deposits carried by drifting ice all preserve the same story, allowing scientists to reconstruct the sequence of events with unusual precision. The beginning of that transformation lay far to the south, where the southern tip of South America slowly drifted away from the Antarctic Peninsula. Plate tectonics, advancing only a few centimeters each year, gradually widened the marine gateway now called the Drake Passage. For an individual lifetime, the movement would have been impossible to notice. Across millions of years, however, the opening became wide enough for an entirely new pattern of ocean circulation to emerge. Cold water was suddenly able to flow uninterrupted around Antarctica, forming the Antarctic Circumpolar Current. Rather than allowing warmer water from lower latitudes to reach the continent, this immense circulating current wrapped Antarctica within a moving barrier of cold seawater. Thermal isolation followed, and the southern continent began cooling far more rapidly than it had throughout the preceding millions of years. Around 33.9 million years ago, that cooling crossed a critical threshold. The East Antarctic ice sheet began to expand across the continent, locking extraordinary quantities of water into growing masses of ice. This development is preserved so distinctly within the geological record that its timing can be recognized across marine sediment cores separated by entire ocean basins. What followed was not merely another episode within a slow climatic rhythm. It marked the beginning of a fundamentally different planetary system. As water accumulated on land in the form of ice, global sea levels declined. Vast, shallow coastal environments gradually retreated, exposing areas that had long remained beneath warm tropical seas. These continental shelves had supported abundant fish, marine reptiles, early whales, and countless smaller organisms throughout the Eocene. Their contraction reduced the productive habitats that had nourished the food web supporting Basilosaurus. Ocean circulation also reorganized in ways extending far beyond Antarctica itself. Cold, deep water circulated more vigorously, carrying nutrients along different pathways while altering the thermal structure of entire ocean basins. Regions that had remained consistently warm became cooler, seasonal patterns shifted, and marine ecosystems began reorganizing from their foundations upward. Species adapted to prolonged warmth encountered conditions unlike those under which they had evolved for millions of years. The tropical seas did not disappear entirely, but they contracted toward the equator, becoming smaller and less continuous than before. The immense warm marine realm that had once stretched across much of the globe fragmented into narrower belts, separated by increasingly cooler waters. An apex predator, built for expansive, shallow oceans, found its preferred environment steadily diminishing. Within the fossil record, Basilosaurus reaches its conclusion at this same boundary. Its remains are abundant throughout the closing chapters of the Eocene, yet beyond the transition, they are absent. The disappearance does not unfold through a prolonged decline extending across many geological stages. Instead, it coincides with the climatic threshold recorded around the world where changing currents, expanding polar ice, falling sea levels, and cooling oceans together reshaped the living architecture of the planet. In the end, the predator did not fail its world. The world itself became something entirely different. The final chapter of Basilosaurus is not merely a story about extinction. It is also a lesson in the difference between two very different endings that often become confused. One is defeat at the hands of a stronger rival. The other is the gradual disappearance of the conditions that once made success possible. The history of this ancient whale belongs firmly to the second path, revealing a distinction that echoes throughout the history of life on Earth. Outcompetition follows a familiar pattern. A new predator arrives with advantages in speed, efficiency, adaptability, or reproduction. Over time, the established hunter loses access to prey, territory, or breeding opportunities until its population shrinks beyond recovery. The struggle unfolds between living competitors sharing the same world, each responding to the presence of the other. Such contests have shaped countless ecosystems, with one lineage gradually replacing another through direct ecological pressure. Obsolescence follows a different course entirely. Nothing stronger needs to appear. No superior hunter is required. Instead, the environment itself transforms until the remarkable adaptations that once guaranteed survival become increasingly mismatched to the changing world. The organism remains exquisitely designed for the conditions that created it, yet those conditions steadily fade away. Excellence becomes irrelevant because the stage upon which it evolved no longer exists. When Basilosaurus vanished approximately 34 million years ago, no known marine predator possessed the ability to challenge it across the warm seas it had long commanded. The sharks of the late Eocene remained considerably smaller and occupied lower positions within the food web. Other members of the Basilosaurid family existed, yet none equaled its immense proportions. The earliest toothed whales and baleen whales had begun their own evolutionary journeys, but they remained relatively modest animals inhabiting ecological roles far removed from the summit occupied by Basilosaurus. Nothing indicates that Basilosaurus was steadily surrendering hunting grounds to competitors. There is no evidence that another predator displaced it from the richest coastal shelves or harvested prey with greater efficiency. Its decline cannot be explained by military language borrowed from human conflicts, because no victorious successor stood waiting to inherit its throne. The greatest predator of its age did not lose a contest against another hunter. Instead, the transformation described through the preceding chapters continued gathering momentum. Warm continental shelves contracted as sea levels fell. Ocean circulation shifted into unfamiliar patterns. Marine communities reorganized from the smallest drifting plankton to the largest vertebrates. Prey populations altered their distribution, abundance, and composition. The ecological architecture that had sustained an enormous warm-blooded hunter across interconnected tropical seas gradually dissolved into something fundamentally different. Basilosaurus had become extraordinarily specialized for a world defined by prolonged warmth, expansive, shallow habitats, and abundant prey spread across nearly continuous tropical oceans. Those adaptations had elevated it to unmatched success for millions of years, yet specialization carries an unavoidable cost. The more completely evolution shapes a creature for one set of circumstances, the more dependent that creature becomes upon their continued existence. Adaptations that once represented perfection can become burdens when the surrounding environment follows a different path. This pattern extends far beyond a single whale lineage. Many of the great extinction events preserved within the geological record reflect changing worlds rather than victorious rivals. The end of the Cretaceous Paleogene extinction, the end Permian extinction, and the Eocene Oligocene transition each transformed the environmental foundations upon which entire ecosystems depended. Dominant species often vanished not because another organism proved stronger, but because the conditions that had defined their success disappeared beneath them. Seen through that broader lens, Basilosaurus leaves behind more than immense bones, preserved within ancient rock. It becomes an enduring reminder that nature measures success only within the world that exists at a given moment. When that world changes beyond recognition, even its greatest master may simply find that there is no longer a place shaped for its extraordinary design. The ocean did not remain empty after Basilosaurus disappeared. Life continued its patient work of adaptation, exploring new possibilities within seas that had become colder, deeper, and governed by patterns of circulation unlike those of the ancient Eocene. The creatures that eventually assumed the highest positions within these transformed waters did not inherit the world of Basilosaurus. They entered a different one, shaped by new opportunities and demanding entirely different solutions. As the Oligocene unfolded, the earliest ancestors of the two great branches of living whales began an extraordinary diversification. One lineage gave rise to the baleen whales, while the other produced the toothed whales. Both emerged after Basilosaurus had already vanished, and both evolved within oceans increasingly influenced by cooling climates, vigorous currents, and expanding deep water habitats. Their defining adaptations reflected these new conditions rather than the tropical seas that had once favored an immense pursuit predator. The ancestors of modern baleen whales abandoned the need for large individual prey. Instead of capturing one substantial animal at a time, they evolved flexible plates of keratin suspended from the upper jaw. Water drawn into the mouth could be forced outward, while countless tiny organisms remained trapped behind these natural filters. Vast swarms of krill, copepods, and small fish suddenly became available as food, transforming abundance itself into the foundation of survival. This remarkable feeding strategy matched the changing planet with remarkable precision. Cold oceans, stirred by increasingly powerful circulation, generated nutrient-rich upwelling that fueled immense blooms of microscopic life. Those blooms supported dense populations of small crustaceans and schooling fish across enormous stretches of sea. Rather than pursuing individual prey through warm shallows, baleen whales harvested entire concentrations of life in great, sweeping mouthfuls, allowing body sizes that eventually exceeded anything the Eocene had produced. The toothed whale lineage followed a different path into the changing ocean. Their greatest innovation was not greater speed or stronger jaws, but an entirely new way of perceiving the underwater world. Through biological sonar, they learned to produce focused sound pulses and interpret the returning echoes, constructing detailed mental images even where sunlight never reached. Darkness ceased to be a barrier. The deep ocean became accessible hunting territory. With this ability came access to prey that Basilosaurus could scarcely have encountered. Squid, deep-dwelling fish, and countless other organisms occupying the immense water column below the surface became available to predators capable of navigating through complete darkness. Vision remained valuable, yet it was no longer the primary guide. Sound itself became an instrument for locating movement, distance, and form across hidden depths. Another transformation unfolded within behavior rather than anatomy. Many toothed whales and several baleen whale species developed increasingly sophisticated social lives. Cooperative hunting allowed groups to surround prey with remarkable coordination. Mothers and relatives protected vulnerable calves through collective vigilance. Knowledge passed from one generation to the next, preserving migration routes, feeding strategies, and vocal traditions that endured long after individual animals disappeared. None of these characteristics represented improvements that would have granted victory over Basilosaurus within the warm Eocene seas. Baleen offered little advantage where enormous prey already flourished across shallow tropical shelves. Biological sonar provided limited benefit within habitats dominated by clear water and daylight hunting. Complex cooperation addressed challenges belonging to oceans whose ecological structure had already shifted beyond recognition. The descendants that eventually came to dominate the world's oceans therefore stand not as perfected versions of Basilosaurus, but as answers to different environmental questions. Evolution rarely advances toward a single ideal form. Instead, it responds to whatever circumstances the planet presents. As climate reshaped the sea, new possibilities emerged, and life followed those pathways with extraordinary creativity. Basilosaurus belonged completely to one remarkable world, while the whales that followed belonged just as completely to another, each perfectly fitted to the age that shaped them. Few prehistoric predators are mentioned together more often than Basilosaurus and Megalodon. Their names have become almost inseparable within popular imagination, as though they belonged to the same age and contested the same waters. Yet the fossil record tells a far more interesting story, one defined not by rivalry but by separation. They occupied the same ecological position at different moments in Earth's history, each ruling an ocean that the other never experienced. By the time Megalodon appeared, Basilosaurus had already been absent for approximately 11 million years. The final representatives of the ancient whale disappeared around 34 million years ago, while the earliest widely accepted fossils of Megalodon date to approximately 23 million years ago. Between those two intervals stretched millions of years, during which marine ecosystems continued changing, climates continued cooling, and new lineages steadily reshaped the living fabric of the sea. Because of this long separation, the two giants never encountered one another. They shared no hunting grounds, competed for no prey, and never tested their abilities against each other. The ocean inherited by Megalodon had already been transformed through climatic change, altered circulation, and the continuing evolution of marine life. It contained creatures that Basilosaurus had never known, living within environmental conditions that would have seemed unfamiliar to the great predator of the Eocene. The differences extended far beyond chronology. Basilosaurus belonged to the mammalian branch of life, breathing air, giving birth to live young, producing milk, and maintaining a warm-blooded body through internal physiology. Megalodon belonged to the cartilaginous fishes, following an evolutionary path that had diverged from mammals hundreds of millions of years earlier. Their skeletons, sensory systems, reproductive biology, and developmental histories reflected entirely separate origins. Any comparison between them rests upon ecological role rather than close biological relationship. In sheer physical dimensions, Megalodon likely exceeded Basilosaurus in overall body mass. Most scientific estimates place the enormous shark between 15 and 18 meters in total length, which is about 49 to 59 feet. Basilosaurus often matched or exceeded those measurements in total body length because of its remarkably elongated form, yet its serpentine proportions complicate direct comparison. One animal resembled an immense, streamlined shark, while the other stretched into a long, flexible whale unlike anything alive today. Similar measurements concealed fundamentally different designs. Their prey also reflected the worlds that had shaped them. Basilosaurus hunted within warm tropical seas populated by early whales, marine reptiles, turtles, and ancient fish communities characteristic of the Eocene. Megalodon entered oceans where baleen whales had diversified into increasingly large filter feeders. These abundant marine mammals became one of the defining food resources supporting the great shark. The rise of enormous baleen whales was itself a consequence of colder oceans and nutrient-rich upwelling systems that had developed long after Basilosaurus disappeared. Even the endings of their stories reveal striking similarities. Megalodon survived for millions of years before disappearing approximately 3.6 million years ago. Evidence suggests that intensifying cooling associated with expanding northern hemisphere glaciation altered the warm coastal nursery habitats used by many large whales, reducing access to the prey populations upon which the giant shark depended. Once again, changing climate reshaped marine ecosystems from the foundation upward. The resemblance between these extinctions is therefore deeper than any imagined battle between legendary predators. Two apex hunters evolved under very different environmental conditions, each becoming exceptionally successful within the world that produced it. Both flourished for millions of years, and both ultimately vanished when planetary climate transformed the oceans beyond the limits of their specialized adaptations. Rather than viewing Megalodon as the successor that defeated Basilosaurus, it is more accurate to see the two as parallel chapters within a much longer history. Each tells the story of a different ocean, inhabited by different creatures and governed by different rules, yet both arrive at the same enduring conclusion. Even the greatest predator cannot outlast the transformation of the world that gave it life. There is a particular kind of ending that reaches beyond the disappearance of a species. It is the ending of an entire branch of life, a path explored by evolution for millions of years before closing forever. Basilosaurus belongs to that rare category. Its extinction was not simply the loss of one remarkable predator, it marked the final page of a lineage that would never produce another descendant. Every species eventually reaches its conclusion, yet many leave heirs behind. A population fragments into new forms, descendants adapt to changing landscapes, and familiar features continue through different bodies across immense spans of time. The history of life is filled with such transformations, where apparent endings become beginnings hidden beneath new shapes. Basilosaurus followed a different course. When the last member of its lineage vanished from the oceans, no surviving population remained to carry its unique inheritance into another age. This outcome becomes even more remarkable when viewed beside the ancestry of living whales. Every whale, dolphin, and porpoise swimming today traces its origin through a separate branch of early whale evolution, one that diverged from the ancestors of Basilosaurus long before the great predator reached the height of its success. Those parallel relatives shared ancient roots, yet they traveled along different evolutionary roads, each responding to different opportunities and constraints within changing seas. The ancestors of modern cetaceans were comparatively modest animals during the closing chapters of the Eocene. They lacked the immense body size, elongated proportions, and specialized hunting machinery that allowed Basilosaurus to dominate warm marine ecosystems across much of the world. In ecological terms, they occupied less commanding positions, surviving beside a predator that appeared vastly more successful within the environment of its time. Yet those smaller branches possessed possibilities that would only reveal their importance after the world itself changed. Within their genetic architecture lay the foundations for increasingly sophisticated hearing, complex communication, advanced social behavior, and eventually the remarkable innovations of baleen filtration and biological sonar. These traits had little advantage in the tropical seas where Basilosaurus flourished, but they became invaluable as cooling oceans reorganized marine ecosystems across the planet. The lineage of Basilosaurus carried its own remarkable collection of adaptations, refined through approximately 15 million years of natural selection. Its elongated body, powerful vertebral column, formidable jaws, and specialized approach to predation represented an evolutionary experiment of extraordinary success. Every generation preserved and strengthened those characteristics because they matched the demands of the warm Eocene oceans with remarkable precision. When the lineage ended, every one of those accumulated innovations disappeared alongside it. No descendant inherited its distinctive body design. No later whale adopted its unusual skeletal proportions. None of its specialized predatory strategies passed into the cetaceans that survived beyond the Eocene. Evolution rarely preserves every successful solution. Instead, it continually tests countless possibilities, retaining only those that remain compatible with changing environments. Basilosaurus had mastered one world completely, yet mastery of one world offered no guarantee within another. This pattern is more common than it first appears. Most species that have ever lived left no descendants at all. The fossil record is filled with branches that flourished brilliantly before ending without continuation. What makes Basilosaurus unusual is not merely that it reached such an ending, but that it did so after achieving prolonged dominance across vast stretches of the ancient ocean. Few apex predators have vanished so completely, leaving neither surviving representatives nor recognizable descendants to carry even fragments of their evolutionary legacy. The oceans that followed were therefore not inherited by the greatest hunter of the Eocene, but by quieter branches that had persisted beyond the center of attention. From those comparatively modest ancestors emerged every living whale, dolphin, and porpoise known today. Basilosaurus remains suspended within the fossil record as the complete story of a magnificent experiment, finished in its entirety, remembered only through stone, and carried forward only in the lessons its disappearance continues to offer. Some inheritances cannot be traced through direct descent. They persist instead as echoes within the deeper architecture of life, carried not by a single family line, but by ancient biological instructions shared across many branches. Basilosaurus vanished without leaving descendants of its own, yet fragments of the evolutionary foundation it shared with living whales continue to shape every cetacean swimming through the oceans today. Long before the lineage of Basilosaurus separated from the ancestors of modern whales, dolphins, and porpoises, all belonged to the same expanding family of early cetaceans. Their paths divided during the Eocene, each branch exploring different evolutionary possibilities while retaining the developmental framework inherited from their common ancestor. That shared foundation remained even as their bodies, behaviors, and ecological roles gradually became more distinct across millions of years of natural selection. Deep within every living cetacean lies a collection of regulatory genes that organize the body before birth. Among the most influential are the homeobox gene complexes, often known simply as homeobox genes, which determine where major body regions develop, where limbs emerge, how the spine is segmented, and how the skull acquires its final proportions. Basilosaurus relied upon these same developmental instructions. Although countless generations separate it from every living whale, the essential genetic language responsible for constructing a cetacean body has remained remarkably conserved across evolutionary time. The greatest differences emerged not because entirely new instructions replaced the old ones, but because existing instructions were regulated in different ways. Evolution frequently modifies the timing, strength, and duration of genetic activity rather than inventing completely new developmental systems. In Basilosaurus, the regulatory signals responsible for hind limb formation had already begun reducing structures that were no longer essential for survival in the sea. The ancient program had not disappeared. It had simply become restrained. That gradual restraint continued through the later history of cetacean evolution. In the descendants of neighboring whale lineages that ultimately survived beyond the Eocene, those same regulatory networks became even more effective at limiting the growth of the hind limbs. What remained visible as small external appendages in Basilosaurus eventually retreated beneath the skin, leaving only modest pelvic bones suspended within surrounding muscles. Every modern whale, dolphin, and porpoise still carries those paired bones, disconnected from the main skeleton, preserving an anatomical memory of a transformation that unfolded across immense stretches of geological time. Embryonic development offers another glimpse into this enduring connection. During the earliest stages of growth, modern whale embryos briefly activate developmental pathways inherited from distant terrestrial ancestors. Limb buds begin to appear before regulatory signals halt their further expansion. The sequence does not recreate Basilosaurus itself, yet it reflects the continuation of the same evolutionary conversation carried through shared developmental mechanisms that have been refined rather than discarded. The forelimbs tell a similar story. Hidden beneath the smooth outline of every modern flipper rests an unmistakably mammalian arrangement of bones. A single upper arm bone connects to paired lower arm bones, followed by wrist elements and elongated digits enclosed within the paddle. Basilosaurus possessed this familiar framework as well, adapted for powerful swimming while still preserving the unmistakable blueprint of its terrestrial ancestry. Modern cetaceans continue to build their flippers from that ancient design, demonstrating how evolution reshapes existing structures instead of beginning anew. In this sense, Basilosaurus survives not as a forgotten ancestor standing directly behind every living whale, but as part of the broader evolutionary landscape from which modern cetaceans emerged. It explored one expression of a shared biological foundation, while neighboring branches explored others. The oceans eventually favored different solutions, yet the underlying developmental language remained common to them all. Each whale gliding through modern seas still carries those ancient instructions, preserving within its earliest growth the distant signature of a world where Basilosaurus once moved through warm waters as one remarkable expression of the same enduring genetic heritage. Measured against the span of a human lifetime, 15 million years appears almost beyond imagination. Measured against the rhythms of the planet, it is an astonishingly brief interval for one of the greatest anatomical transformations ever recorded. Within that comparatively narrow window, a lineage of land mammals crossed the boundary between shore and sea, abandoned life on solid ground, and ultimately produced Basilosaurus, an apex predator whose body bore almost no resemblance to the small terrestrial ancestor from which the journey had begun. This transformation is no longer reconstructed from scattered fragments alone. The whale fossil record has become one of the most thoroughly documented evolutionary sequences in all of paleontology, allowing researchers to estimate the pace of body size increase, limb reduction, and ecological specialization through carefully tested phylogenetic methods. Rather than relying upon speculation, these studies compare anatomical change across successive branches of the family tree, revealing how rapidly different characteristics emerged as natural selection acted upon changing populations. Among major vertebrate transitions, the early cetacean lineage stands out for its remarkable speed. The increase in body size documented across these early whales ranks among the fastest known for any large-scale anatomical transformation preserved in the fossil record. It exceeded the pace observed during the diversification of many mammal groups following the Cretaceous-Paleogene extinction and rivaled only a small collection of other exceptional evolutionary radiations. The shift from shoreline hunter to dominant marine predator unfolded with an efficiency that continues to attract scientific attention because it demonstrates how rapidly profound change can occur when ecological opportunity is abundant. The apparent length of 15 million years becomes even more striking when compared with slower geological processes that continue today. The Himalayan mountains have been rising for approximately 50 million years, and their uplift has not yet reached its conclusion. The Atlantic Ocean has been widening for roughly 200 million years as tectonic plates continue their gradual separation. Even the modern course of the Amazon River is believed to be younger than the disappearance of Basilosaurus. Against those immense spans, the transition from wolf-sized terrestrial mammal to giant ocean predator unfolded with extraordinary momentum. Evidence for that progression is unusually complete. Pakicetus appears in rocks dating to approximately 53 million years ago, already displaying characteristics linking terrestrial mammals with future whales. Ambulocetus, followed by approximately 49 million years ago, combining competent swimming with the ability to move across land. Rhodocetus emerged by approximately 47 million years ago, showing further commitment to marine life through changes in the pelvis, limbs, and spine. By approximately 41 million years ago, Basilosaurus had fully established the elongated, ocean-adapted body that defined the culmination of this remarkable sequence. Perhaps the greatest strength of this record lies not merely in its completeness, but in the history of its discovery. Evolutionary theory predicted that intermediate forms should exist between terrestrial mammals and fully marine whales. Long before many of those fossils had been uncovered, paleontologists anticipated where such transitional species ought to appear within rocks of the appropriate age. As exploration continued across Asia, Africa, and other regions preserving ancient coastlines, those predicted intermediates emerged in precisely the sequence expected. Each new skeleton added another chapter rather than overturning the story already taking shape. Basilosaurus therefore represents far more than the final predator in an extinct lineage. It stands as the visible culmination of one of the clearest evolutionary narratives preserved anywhere on Earth. Its bones demonstrate that life does not advance through sudden leaps detached from history, but through countless incremental changes accumulating across generations until the finished result appears almost impossible when viewed beside its distant beginning. Within that extraordinary transformation rests a reminder that evolution, given opportunity and time, can reshape familiar forms into creatures that seem to belong to entirely different worlds. Some names become larger than the creatures they describe. Over time, they gather memories, expectations, and familiar images until the word itself feels as though it defines the animal. Few names carry that kind of weight more strongly than whale. By the time Basilosaurus enters the story, that familiar picture begins to dissolve, revealing how easily the human mind mistakes modern experience for timeless truth. For most people, the word whale summons an immediate collection of associations. Immense bodies drift through open water with deliberate grace. Long songs travel across entire ocean basins. Families remain together across many years, passing knowledge between generations through sound, behavior, and shared experience. Intelligence, cooperation, and emotional richness have become inseparable from the modern image of these marine mammals because the living species most often encountered embody precisely those qualities. Yet Basilosaurus belongs within the same evolutionary lineage despite presenting a remarkably different way of being a whale. By every rigorous standard used in biological classification, its identity is unambiguous. It was a cetacean. It breathed air through lungs rather than extracting oxygen from water. Its young developed within the mother's body before live birth, and those offspring were nourished with milk. Its skeleton retained unmistakable mammalian characteristics inherited from distant terrestrial ancestors. Every major anatomical feature places Basilosaurus securely within the whale lineage, even if almost every familiar expectation attached to that word begins to fail. The classification itself has never been the true source of uncertainty. The uncertainty arises because human language naturally blends ancestry with appearance and behavior. When the same word is applied to a humpback whale and to Basilosaurus, the mind often assumes that both creatures must also resemble one another in temperament, intelligence, and daily life. The fossil evidence offers little support for that assumption. The brain of Basilosaurus appears comparatively modest beside those of many living cetaceans, lacking the expanded proportions associated with the sophisticated cognition seen among modern dolphins, orcas, and several large whales. Nothing presently known suggests elaborate social organization, prolonged cooperative hunting, or the transmission of learned traditions across generations. Instead, the available evidence points toward an animal whose success depended primarily upon physical capability, instinctive behavior, acute senses, and overwhelming predatory efficiency. It was a solitary hunter shaped by immediate ecological demands rather than by intricate social relationships. That contrast does not diminish Basilosaurus. Instead, it expands the meaning of the lineage to which it belonged. Evolution does not move toward a predetermined ideal, replacing primitive creatures with superior versions of themselves. It continually reshapes populations according to the conditions surrounding them. The characteristics admired in modern whales emerged because later oceans rewarded communication, cooperation, deep diving, and increasingly specialized feeding strategies. Basilosaurus occupied an earlier chapter, when different environmental pressures favored an entirely different combination of traits. Seen from that perspective, the category itself becomes more revealing than the individual animal. Human classification provides useful boundaries for organizing the living world, yet evolution recognizes no such neatly defined compartments. Between one familiar form and another lies an unbroken continuum of gradual change, with extinct species often occupying positions that seem unexpected or even contradictory. Fossils repeatedly remind us that the labels created by science describe branches within a continuous history rather than isolated designs created independently of one another. The word whale, therefore, embraces a remarkable range of possibilities. It includes singers whose voices travel across immense distances, highly social hunters coordinating their movements through sophisticated communication, and immense filter feeders sustained by tiny drifting prey. It also includes the elongated predator that once dominated the warm seas of the Eocene, living largely through instinct and physical mastery. The single name remains scientifically correct in every case, even as the image it awakens shifts with each new discovery, becoming broader, deeper, and more faithful to the extraordinary diversity contained within a single evolutionary family. There are moments in natural history when the disappearance of a species tells only part of the story. Basilosaurus belongs to one of those moments. Its bones do not simply mark the end of a remarkable predator, they mark the closing of an entire version of Earth, one whose landscapes, waters, and living communities have vanished so completely that no place on the modern planet can truly be called its equivalent. Extinct animals are familiar to paleontology. Countless branches of life have reached their conclusion, leaving descendants to inherit altered environments or allowing unrelated creatures to assume similar ecological roles. That pattern repeats throughout the fossil record with almost rhythmic regularity. Yet the world occupied by Basilosaurus escaped that pattern in an important way. It was not merely emptied of its dominant hunter. The environmental stage upon which every part of its existence depended disappeared as well, replaced by conditions built according to entirely different rules. The warm waters of the ancient Tethys Sea once stretched across regions that today seem impossible to reconcile with such a setting. Through the immense movement of tectonic plates, that broad tropical seaway gradually narrowed and fragmented. Portions endured as the Mediterranean Sea and the Black Sea, while other fragments became enclosed inland waters such as the Caspian Sea. Vast sections of the former seafloor did not remain beneath the ocean at all. They were folded upward into the growing Himalayas and the Alps, transformed from marine sediments into towering mountain ranges where marine fossils can now rest thousands of feet, which is about 914 meters above present sea level. Elsewhere, the broad continental shelves that once supported flourishing marine ecosystems experienced an equally profound transformation. Areas that had lain beneath warm coastal waters emerged through uplift, erosion, and shifting shorelines until they became dry land. Regions that now include the Sahara, the Arabian Peninsula, and broad parts of Pakistan preserve traces of that vanished seascape beneath layers of rock and sand. Their present appearance bears almost no resemblance to the environments in which Basilosaurus pursued prey across sunlit shallows and expansive coastal waters. The living community surrounding that predator also faded beyond recovery. Dorudon disappeared. Many early relatives of modern sea cows vanished without direct continuation. Entire families of fishes passed from existence, taking with them ecological relationships that can now be reconstructed only through scattered fossils preserved within the same ancient sediments. Even where distant relatives survive, the intricate network of interactions that once connected predator, prey, scavenger, and habitat can never be restored in its original form. The transformation reached beyond geography and biology into the character of the water itself. Ocean circulation followed different pathways across the globe. Patterns of salinity varied from those familiar today. The balance of dissolved gases shifted with changing climates and currents. Tiny differences in chemical composition became locked within shells and bones, leaving isotopic signatures that modern researchers can still read as subtle records of vanished seas. Those delicate chemical traces reveal an ocean that obeyed conditions unlike those governing the modern world. When a skeleton of Basilosaurus emerges from the Egyptian desert, it therefore carries a meaning that extends beyond the animal alone. It is not simply a fossil transported through time. It is a surviving fragment of a planetary chapter that reached its conclusion long before human beings appeared. The surrounding landscape belongs to a different Earth, shaped by different climates, different continents, and different oceans. The stone embracing those bones has become more than a container for ancient remains. It serves as the final archive of a world that cannot be revisited except through careful observation and patient imagination. What survives is not merely evidence that life once looked different. It is evidence that Earth itself has lived through many identities, each complete in its own time, each eventually yielding to another, while only the most enduring traces remained to tell the story. Across the immense sweep of Earth's history, the rise and fall of Basilosaurus begins to resemble something larger than the biography of a single species. It becomes part of a recurring rhythm, one that has echoed through oceans, forests, deserts, and skies for hundreds of millions of years. The names change, the continents drift, and the climates transform, yet the underlying pattern remains remarkably consistent. A lineage achieves extraordinary success because it becomes exquisitely suited to the conditions surrounding it. Every refinement of anatomy, every improvement in behavior, and every advantage in physiology strengthens its position within that particular world. Specialization brings efficiency, dominance, and endurance. Yet the same adaptations that create supremacy also narrow the range of environments in which that supremacy can exist. The closer a species approaches perfection for one set of circumstances, the more dependent it becomes upon the continued existence of those circumstances. Long before mammals entered the oceans, trilobites occupied marine ecosystems across the Paleozoic era for nearly 270 million years. Few groups have maintained such prolonged success. They diversified into astonishing forms, inhabiting countless ecological niches while seas repeatedly expanded and retreated across the continents. Their persistence seemed almost permanent until the profound environmental upheaval at the close of the Permian period reorganized ocean chemistry, circulation, and habitat on a planetary scale. The conditions that had sustained them dissolved, and with those conditions vanished the lineage itself. The same broad rhythm appeared again among the non-avian dinosaurs. For approximately 165 million years, they dominated terrestrial ecosystems with extraordinary variety, ranging from feathered hunters, scarcely larger than birds, to towering herbivores that reshaped entire landscapes through their feeding. Their disappearance did not arise because another group gradually surpassed them in strength or intelligence. A rapidly changing global environment following the Cretaceous-Paleogene extinction transformed climate, vegetation, and food webs faster than their long-established specializations could accommodate. Much later, another marine hunter would follow a remarkably similar path. Megalodon became the supreme predator of warm seas during the Miocene and Pliocene, thriving within productive coastal environments that supported abundant marine mammals. Its enormous body and formidable jaws reflected precise adaptation to those conditions. As climates cooled and warm nursery habitats contracted, the ecological foundation supporting its preferred prey diminished. The predator itself was left exquisitely suited to an ocean that was steadily disappearing beneath changing currents and temperatures. The present ocean contains its own masters. Orcas combine sophisticated communication, cooperative hunting, cultural learning, and remarkable behavioral flexibility into one of the most capable predatory lifestyles known. Great white sharks have persisted through immense spans of geological time with body designs that remain strikingly effective. Both continue to flourish across broad regions of the modern sea, yet neither exists outside the influence of planetary change. Ocean warming, shifting prey distributions, increasing acidity, and reorganizing ecosystems introduce pressures unlike those that shaped the long evolutionary histories of these living predators. Recognizing this pattern does not require predicting specific futures. The fossil record offers something subtler and more enduring than prediction. It reveals repeated relationships between environmental transformation and biological success. Again and again, the dominant hunter of an age prospers only while the world that shaped it continues to exist in recognizable form. When that world changes beyond certain limits, even extraordinary adaptation becomes insufficient. Basilosaurus therefore occupies a place within a much longer narrative, extending far beyond the Eocene. Its story is joined to those of trilobites, dinosaurs, gigantic sharks, and countless other rulers whose reigns once appeared unshakable. None were defeated simply because another creature proved stronger. Each flourished for as long as the planet continued writing the chapter to which it belonged. When the chapter closed, the inhabitants passed with it, leaving behind fossils that reveal not failure, but the enduring truth that life and Earth have always changed together. Some spans of time resist ordinary intuition. 15 million years belongs among them. It is a duration so immense that mountain ranges shift, coastlines wander, and entire climates are rewritten while a single successful lineage continues to endure. Against the scale of a human lifetime, it seems almost without end. Against the age of the planet, it is only one chapter, yet it is a chapter long enough for Basilosaurus to become one of the most enduring apex predators the oceans have ever known. No living marine hunter approaches such a tenure as a recognizable species. Modern orcas have likely existed for only about 2 to 3 million years. Great white sharks, in their present form, have persisted for perhaps 4 million years. Both are extraordinarily successful by any biological standard, yet even together they do not approach the length of time during which Basilosaurus remained one of the defining forces of the Eocene seas. Its reign lasted through countless generations, through gradual continental movement and shifting coastlines, before finally reaching its natural conclusion. Yet duration, however astonishing, offered no exemption from impermanence. Basilosaurus disappeared completely. No remnant population lingered in an isolated sea. No closely related descendant continued its particular way of life. The branch itself came to an end, leaving only fossilized bones, and the deeper developmental inheritance shared through far older common ancestry with the whales that would later flourish. Its own lineage ceased, while neighboring branches continued their separate journeys through evolutionary time. This is not a story of failure. Evolution recognizes neither ambition nor defeat. It measures only persistence and reproduction within changing environments. By those standards, Basilosaurus achieved remarkable success. It occupied oceans around the globe. It maintained ecological dominance for 15 million years. It produced enough individuals across enough generations that their remains now appear on multiple continents, allowing paleontologists to reconstruct its anatomy, behavior, and history with unusual confidence. Few extinct animals leave behind such an abundant and coherent record. The deeper lesson emerges not from its disappearance, but from the conditions surrounding that disappearance. Dominance has never been an absolute quality. It has always depended upon a particular world existing in a particular state. Basilosaurus did not become perfectly suited to warm Eocene seas through foresight or intention. Across innumerable generations, natural selection refined every aspect of its body to match the opportunities presented by that environment. The very adaptations that elevated it above every competitor also tied its future to the persistence of the world that had shaped them. When that world changed beyond certain limits, no amount of previous success could preserve the form built for its vanished conditions. Adaptation had reached extraordinary precision, yet precision itself became constraint once the surrounding environment followed a different path. What had once represented unmatched biological excellence no longer aligned with the reorganized oceans emerging across the planet. Looking farther across geological history reveals that this relationship repeats with remarkable consistency. Before Basilosaurus, armored fishes, marine reptiles, and countless forgotten predators occupied comparable positions within ecosystems that no longer exist. After Basilosaurus, other rulers inherited transformed seas, among them the gigantic shark known as Megalodon, itself destined to disappear when another climatic chapter closed. Today, orcas and great white sharks occupy prominent positions within modern oceans, each magnificently adapted to present conditions rather than eternal ones. The fossil record offers no permanent throne. It reveals only successive worlds, each producing creatures exquisitely fitted to their own moment, before yielding to another arrangement of continents, currents, climates, and life. Basilosaurus therefore leaves behind a conclusion both gentle and enduring. Nothing in nature remains supreme forever, not because greatness fades, but because the living planet continues to change, carrying every dominant lineage forward only for as long as its world continues to exist beside it. Across the western desert of Egypt, the landscape continues a patient conversation with time. Grain by grain, the wind wears away sandstone that began as warm Eocene seafloor, exposing fragments of skeleton that have rested within stone for 34 million years. Nothing hurried their return. No witness was required. The rock simply loosened its hold until vertebrae, ribs, and jaws emerged once more beneath an open sky that bears almost no resemblance to the sea that first received them. Those bones have endured through changes beyond ordinary imagination. They remained buried while the Tethys Sea vanished from the map of Earth. They remained while continents drifted into new positions and mountain ranges climbed from former seabeds. They remained through repeated advances and retreats of continental ice, through the appearance and disappearance of countless species, through climates warmer and colder than those familiar today. The mineral framework of a single skeleton persisted while almost everything surrounding its existence was rewritten. Yet endurance has its own boundary. The bones survived because stone protected them, but the living world that once gave those bones purpose did not. No current shoreline preserves the exact waters through which Basilosaurus hunted. No surviving food web recreates the intricate relationships that sustained its immense body. The currents, chemistry, temperatures, coastlines, and communities that shaped its life dissolved into geological history. Fossils preserve form with remarkable fidelity, but they cannot preserve the complete living fabric that once surrounded them. This becomes one of the gentlest paradoxes within paleontology. The hardest parts of an organism may outlast the organism itself by spans almost beyond comprehension, yet even they cannot preserve the full reality of the vanished world from which they came. A vertebra reveals strength. A tooth suggests diet. The shape of a skull hints at senses and behavior. Between those fragments stretches an ocean that no excavation can entirely recover. The imagination may approach it. Science may steadily refine it, yet some portion remains forever beyond direct reach. Meanwhile, the modern sea continues with its own remarkable inhabitants. Orcas pursue prey through cooperation refined across generations. Sperm whales descend nearly 2 kilometers, that is nearly 1.2 miles, beneath the surface where sunlight never reaches, guided by biological sonar through immense darkness. Great white sharks detect faint electrical signals carried through seawater, perceiving movements hidden from ordinary sight. Each represents an extraordinary solution to the demands of the present ocean, every adaptation matched to conditions existing now, rather than those that shaped the distant Eocene. None of these creatures possesses any memory of Basilosaurus. Evolution does not preserve recollection. It preserves only the living lineages capable of continuing through changing environments. The greatest predator of one age leaves no awareness within the greatest predator of another. Each world begins with its own opportunities, fashions its own rulers, and eventually yields them to another chapter whose inhabitants inherit a different planet than the one before. Perhaps this leaves only a single reflection worthy of carrying forward. Every age naturally assumes that the surrounding world is familiar because it has always appeared that way within living memory. The fossil record offers another perspective. Oceans change, continents move, climates reorganize. Dominant creatures flourish for astonishing lengths of time before yielding, not because they lacked greatness, but because the stage beneath them gradually became another place entirely. Basilosaurus never anticipated such change. It lived completely within the conditions that shaped it, as every species does. When those conditions faded, its body entered the sediments of a retreating sea, and the planet continued its long transformation. Now the desert uncovers those ancient remains once again, not as monuments to power, but as enduring reminders that worlds themselves possess lifetimes. 15 million years of complete ocean dominance became stone beneath the sand, and after everything else had passed away, those weathered bones remained, carrying the last tangible memory of a sea that no longer exists.